Hi, my name is Manish Gupta, and in this video, I'm going to talk about this interesting paper, Do Androids Laugh at Electric Sheep? Right? In fact, this is a paper on understanding how much the large language models can understand humor, and it is, in fact, it was awarded the Best Paper Award at ACL 2023. So let's get started. Can LLMs understand humor? That's the basic question. So to be able to look at this problem in a more interesting manner, the authors looked at these New Yorker strips. So each week, the New Yorker publishes an uncaptioned cartoon image. So they just provide this image, inviting readers to submit their funniest English language caption for it. So several readers submit those captions, thousands of them sometimes. So editors actually choose three finalists from these thousands of submissions, and then the readers vote to pick the final winner. So that's the two-stage evaluation process. People submit, editors final choose top three, and then readers pick the top one, the best one, right? So now, based on this kind of a data set, so the data set looks like this. It has several hundreds of cartoon images, and then several annotations on top of them. In fact, the authors propose like three interesting machine learning tasks based on this data. Matching, ranking, quality ranking, and explanation. Matching, quality ranking, and explanation generation. So here are the three tasks. So matching. So, the idea is that you provide five different captions for the image to the model, and then ask the model to choose the best one. So that's that. So essentially the five that were chosen here, of course, the most rated one, the picked one, the finalist one is of course chosen as the one of the alternatives, and the other four are randomly chosen from the data set. Okay. The second task is quality ranking task. So the idea is that you have two different captions, and the model is supposed to choose which one fits better for this particular cartoon, right? The third one is explanation generation task. So, if you think about a friend who did not get the cartoon and get the humor in the caption associated with the cartoon, then how would you explain to your friend, right? So that's basically the explanation. Okay. So maybe we can look at this example. So this example basically shows a couple of animals in some forms, sitting on a table and they're discussing. The best chosen caption is publicly we are still saying that there are no side effects. So of course, this is people from a pharmaceutical company who have probably tried out a drug, and then they figured out, oh, it has so many side effects, but still they're trying to say that, hey, we will never admit publicly that the drug has any side effects, right? So, the caption that wins is publicly we are still saying that there are no side effects, and here is a reasonable explanation. There's a board meeting going on of some shady pharmaceutical company, and the drug the company makes has side effects of turning people into monsters. But then they are choosing to not warn the public, right? So that's that. So this is the interesting setup in which the authors experiment and try to evaluate how good our large language models are at doing these three tasks: matching, quality ranking, and explanation generation, right? And while you can do this task by giving the model only the image, that task is very difficult for large language models. So therefore, what they try to do is to also generate some manually annotated text data associated with the image cartoon, and also provide that to the large language model, right? So to be able to do that, they spend a lot of time in getting more annotations for these cartoons. So the idea is that human annotators were given image, just the image, and they were asked to generate these four things, these four different forms of text metadata associated with the cartoon. Okay, so these four things, of course, the first one, as you see here, in this cartoon, it's a science lab or a laboratory. So that's a phrase which is describing the setting of the scene. For example, an office or park. In this particular case, science lab or laboratory. In the lower case, it is doctor's office. That's that. Okay. The second one is basically, yeah, the second metadata is a literal 1 to 3 sentence description of the scene. Give a 1 to 3 sentence description of the scene. So, a mouse is wearing a jetpack and cheating at a maze. Two scientists stare at him. So that's a description, or on the description. Two scientists are observing a rat making its way through a maze to find the cheese. The rat is operating a jetpack to skip the maze and go straight to the reward at the end. Okay, so that's basically another description. The third one is basically an uncanny description, basically a 1 to 3 sentence description or explanation of what makes the scene unusual. Why is it unusual? What is funny about it, right? So a mouse is wearing a jetpack to cheat at the maze. Mice are not that intelligent, right? And a rat has learned to build and operate a miniature jetpack, right? So that's basically, what is funny or unusual about this. Right? And then the fourth metadata is 2 to 3 English Wikipedia links. As you see, these are English Wikipedia links that an annotator identified as relevant to serve as a proxy for world knowledge. So of course, explaining jokes requires world knowledge also. So, for example, here, understanding what is a jetpack, what is, of course, a mouse or a maze or laboratory mouse or Tryon's rat experiment. Those are all reasonable Wikipedia links. So for this one, it's basically physical examinations, stethoscope, and of course, what's funny is basically nobody examines safes, right, or things inside a safe rather than living beings. Okay, so that's the extra annotations, text annotations that are manually curated. Okay. So now, of course, the $1 million question: how well can LLMs understand humor? Can androids laugh at electric sheep really? Right. So, and here are some results. So there are two tables here. So in the first table, essentially the results are shown for matching and for quality ranking. In the second table, the results are shown for generation, right? Text explanation generation. So how well models can generate explanation. Yeah. So of course, so what you see here is a three matrix, or rather, accuracy, matching accuracy. So that's basically just accuracy. So, matching task is a 5-class classification task in that senses. So matching accuracy. Quality ranking is a binary task in that senses, but what you see here is crowd accuracy or New York accuracy. So New Yorker accuracy is basically accuracy based on the New Yorker editors, while crowd accuracy is the accuracy based on finalists, basically decided by the crowd. Okay? So, and what you see here is baselines, random and caption only baselines. So caption only basically means they just fine-tuned T5 11 billion model by just giving the caption. The image was not provided at all. So this is just the text only thing, right? So, just give the caption, and then you have no knowledge of the cartoon at all. And I mean, can the model still predict something from the caption? That's the idea. Yeah. The second block is the more realistic block, which is basically from pixel setting, as they call it. Here, the models are actually at train time, they are given the cartoon and, of course, the matching caption, right? Or essentially, even from a quality ranking perspective, they are given the cartoon and the other captions, matching caption and the negative ones also, and you basically learn using some contrastive loss. Right? That's the loss using which you fine tune. Okay. But at test time, you basically just give the image, because at test time you have to you have to basically say whether a caption is good or not, right? So essentially, at test time you just basically give the image. Okay. So that's that. Now, however, there are also these sort of oracle, semi-oracle kind of models, from description models, where you just don't give the image, but you also give the description. That basically helps the model understand the image from a human-centric perspective. So in these FT from description kind of models, you simulate the access to the image, or you simulate the access to a human-level computer vision system. Of course, you just don't give the image, but or rather, you don't actually give the image, but you give what the human understood. For example, if the human understood that this is a science lab setting, and if the human understood what is unusual is a mice, being able to operate a jetpack and so on, you give that. So you give a fairly good enough understanding of the image as part of the input to these from description models. Note that this is, of course, an oracle setting. You will not really have that to be able to participate in the New Yorker contest. So that's the settings. Now, what you observe. So there are interesting observations. The first thing, of course, is the GPT-4 model, and they experiment with several models, right? So experiment with the clip model, OFA model for the vision settings, and then they experiment with several text-only models like T5 model and GPT models. And they find that GPT-4 with 5-shot prompting actually gives them the best results, right? Gives them the best results. So that's that. Now, amongst the from pixels, the vision-based models, which is basically the real setting, right? Not the oracle setting in that sense, is fine-tuning clip helps. So they could also experiment with 0-shot clip, but they found that fine-tuning clip gives better results. And They also observed that while fine-tuning clip gives better results from a quality ranking perspective, or rather from a crowdsource accuracy quality ranking perspective, they also found that OFA model gives you reasonable results. But in either case, if you compare with the human accuracy, so the last one is human accuracy, human estimate, right? When people just look at images and they're given 5 captions, how well can they figure out which one is the most matching, or how well can they, an average human can figure out what is going to be, which of the 2 captions is better in terms of quality, right? If you look at that, right, the models are nowhere there. So 62.3 versus 94, 57, or maybe the best is 60 versus 83, 66.9 versus 64.6. So yes, from this perspective, maybe it is good. From New Yorker editor accuracy perspective, it's sort of good. But if you look at the other 2 metrics, the LLMs actually are 30 points behind, almost 30 points behind, human accuracy. So the takeaway is that the best multimodal models still fall 30 accuracy points behind the human performance on the matching task, and even when provided ground truth. So in these FD models, you're providing ground truth visual scene descriptors. They are still not as good, and they're still way behind human accuracy, right? So there's a lot of room to cover. There's a lot of room to make these LLMs understand humor. They also did human evaluation of the explanations generated by these models. And they found that the last one is the most interesting. If you compare the human explanations with the best 5-shot GPT-4 model, they still find that the humans win 2/3 of the times. Only 1/3 of the times, basically, you have the GPT-4 kind of models being able to compute, to come up with explanations that are worthy enough. But otherwise, 2/3 of the times, human explanations are better compared to GPT-4. Okay, so even in terms of generating explanations, LLMs are not there yet. Okay. However, they also did several other experiments from an explanation generation perspective, and they found that in general, passing on fine-tuning, right? Fine-tuning with descriptions is way better compared to just using captions. Also, if you basically leverage these descriptors, human-generated descriptors, that's better than depending on LLMs to understand the humor in images directly, right? Of course, the large scale of the models helps. So T5 large is better, or rather, yeah, T5 11 billion is better than the T5 large, right? Fine-tuning helps. So fine-tuning, or rather, but then fine-tuning does not help much. So essentially, 50% wins, basically saying that yes, whether you do fine-tuning with GPT-3 or just do in-context GPT-3, zero shot in that senses, that doesn't differ much. But if you look at 5-shot, so in context learning, however, with few shot learning actually gives you better results, right? Similarly, if you look at GPT-4 versus GPT-3, GPT-4, of course, is known to be much better quality than GPT-3, and they also verify that in terms of this human understanding task. So in summary, this was a very interesting paper, won the best paper award at ACL 2023. What it shows is that today's large language models still cannot really understand humor. They cannot recognize caption relevance, evaluate, or explain New Yorker caption context as effectively as humans can do. However, there is still some good, interesting, positive output that the partial capacity of today's AI is still substantial and may be sufficient for models to serve as creative collaborators, for example, as brainstorming assistants for humorists or cartoonists. Right? So that's that. They make all of their annotations, models, leaderboard code, everything sort of publicly available. So you can go have a look at that. Thank you for watching. Hope you liked the video. Connect with me on my LinkedIn or look at my research on my home.